Good morning. It's Monday, the 28th of April 2025. You're welcome back. Weather is good, dry outside, but the ground is wet, very, very wet after a lot of rain. I'm going to deal here with capacitors, and I want to put this video along with my other three videos on the subject of electricity, because it is important in many ways, but I have a few inquiries there and people wanting me to deal with it. It's a special interest. If you're not into it, maybe you better turn off and not bother looking at it. I can't just do videos for one particular interest. We have to have a wider interest than that. Now, just to show you the sort of stuff, in many ways, I suppose I should have went on to be some type of an engineer, but that's not how life worked out. I was feeding calves and things like that and going mad fishing and hunting and stuff. But I always had books. Some of these books are extremely old. Some of these are 20, 30 years old. There's an excellent book, Model Engineer's Handbook. Tubal Cain, I think he's a man called Bradford. Tubal Cain is a kind of one of them generic names for some kind of an engineer that existed long ago. And it's special interest publications or some of those. Yes, it's next to special interest publications. It's not very expensive and it contains an awful lot of very useful information on engineering. Anyway, I wouldn't be without it. And included in it is how to convert a three-phase no voltage switch to a single-phase no voltage switch. You have it there without having to experiment yourself. That's very good. Another book I have for years and years is Motors as Generators for Hydropower, Converting a Motor to a Generator. And that's by Nigel Smith. I have that for years. Modeled low plug engines, making small engines. Another one, some of those special interest publications. And T Publishing. And this fella is Lieutenant Colonel G.E. Baldwin, if you don't mind. The art. So you see, there's an army man. You see the you never know where people are interested in these things. Just because a person is a doctor doesn't mean he can't have an interest in something else. And this is Foundry Work for the Amateur by Henry Aspen, and Model and Allied Publications for Argos Books. Foundry Work, never did any of that, but I might get around to that sometime. The Art of Welding by W.A. Wass. They're usually either English or American or Australian, English speaking. That's the problem. You see, the Germans probably could give good books too, but you see, you have the language problem, so it's a bit difficult. And this is Shapers here. Don't know who wrote that book on Shapers. So, I mean, the amount I spent on books, I say €100 even, €100 yet would buy a lot of books. And I have those books for years and years. And if I was sick or something, or I was stuck somewhere where I couldn't get away or going away to a wedding and I had to spend a few hours, I'd bring one with me and give it a read. And then there's other magazines like Model Engineer and Engineering in Miniature, and they're a bit hard to get, but anyway, I do have them there. I get another one from Dublin now and again. Now, on the subject of capacitors, before I start, this is a capacitor out of a microwave oven, and there are unbelievable warnings on these. Apparently, these can be charged up using a transformer to 2000 volts, and if they discharge into your body, they can kill you. So I only have this here as for experimental purposes. I might break it up, but it's discharged. Now, any capacitor should be discharged before you touch it with your fingers. So essentially, if you put your fingers in there to this and it charged, it could kill you. There's warnings on them. So the best way to discharge them is I use a plastic electric fence post. There's a big white one, not the little metal one with the wee curly tail on the end of it. You need plenty of plastic between you and the metal part. There's a white one that goes down on the ground. There's only about that length of a metal part, and then there's a big long post. That's the right one. A dry one of those. If it's a steel one with a bit of a cover on it, it's not as good. So anyway, dangerous. You don't want any connection. So be very careful with them. I wouldn't have those. I wouldn't have them around where there are children or anything. You wouldn't know. You wouldn't know if you're taking a microwave asunder. Be careful of that. Now I do take the magnetron out of the microwaves, and I dump everything else in landfill, for the purpose. But I take the magnetron. There's a very, very good magnet in a microwave oven. There's no point throwing them out. Magnets don't take up too much space. Now, a thing about it is that if you have a house and you have children or anyone else, it's no harm to show your kids how to throw the electricity off. There's usually a switch somewhere on the board, and if you pull it down, it knocks off the whole lot. Put the lights on some night and just show the kids, pull down that switch, bring over a chair and pull it down. Because if there's an emergency and they're there, they pulling down that switch and cutting off the whole power can never do any harm, and it could do a lot of good. Does that make sense? Something we don't think about. Anyway, I don't like to be preaching. Now, so a capacitor has two plates. It has two plates. We'll get the two books here. We'll get this here. And the two plates are made of a conducting material such as aluminium or steel or tin or whatever, or copper. And they're brought very closely together, but they must not touch. If they touch, it's just a conductor. If there's a slight space between them, they then act as a capacitor. And you can have air between them, you can have them out in space in a vacuum, and the actual best capacitor is in a complete vacuum, so there's nothing between the two, okay? Now, in reality, that's very hard to get and keep, so what to do is to put in another sheet in between it, known as a dielectric, and it insulates them, but allows them to go very, very close together, and the electrons come out into the dielectric and they pass between. Now, one of the things about this subject is it proves that atomic science is correct. I might do more about atoms and that, but I don't like to be too highfalutin really. But an atom has a proton and usually a neutron. An atom has a proton and an electron, and the electrons and protons are balanced. So if it's steel with 26 electrons, it'll have 26 protons. If you force the electrons out of there and reduce the amount or increase the amount, you create a potential across the two. So what happens is when you connect your capacitor, the electrons flow into the other one, creating an imbalance. So you have too many electrons this side and not enough here. And when they get a chance, they'll rectify that. And if you do it correctly, the only way they can rectify it is by getting out through a wire from one to the other. Okay, that's basically it. So I've often helped students, third level students, with their projects, give them advice and help them how to do it. Not actually do it myself, but some projects you do require a lathe. But they have to declare it. If they get your help to make something and they can hire you technically to make the part on the lathe, but they must disclose it to the lecturer. But they must design it. So strictly speaking, the person doing the work for the project for the third level course must declare where it was done, how it was done, and this is what we ordered up, and this is what we got back, and now we're showing it working. So that's all right. Now, so here is a capacitor, was done as a school project. I want you to see it there. It's about 28 inches in length. And the way you make this, funny enough, the materials to make a capacitor are freely available. You need greaseproof paper, which is slightly wider than the aluminium foil. You need aluminium foil, which is slightly thinner, obviously. And then you need some kind of ordinary wrapping paper with no metallic content, ordinary plain wrapping paper, and elastic bands are important as well. And you need two pieces of wire to make the connectors. Here they're here, and they should be, do you see that's white copper wire? They should be with plenty of fuzzy copper wire, nice flexible copper wire. So if you get a bit of cable for a light bulb or that, don't have it solid copper wire, have it with plenty of little strands in it. And you'll know if they're not. Some of the copper now in cars has steel to cut down costs. No good. Use proper copper wire. Now, what you do then is you really need to go to a gym or something that has a smooth wooden floor and sweep it. Or if you got the local community centre that they let you in there when there'd be nobody using it on a Sunday morning, something smooth. Doing it out on a stony yard is not on, and you won't do it in your house because you need such a long piece. So you buy Turkey aluminium foil, which is, make sure it's thick, its width is a little less. First of all, buy the greaseproof paper, wide Turkey greaseproof paper for cooking. Then bet your foil and make sure the foil is thinner, does not extend out over the edges. and then you put your greaseproof on the floor, you put your aluminium on top of it, and with this length you need about 10 meters, because these homemade capacitors are not efficient, so you need about 10 meters. No point doing a little small one, only this size. A capacitor that size with that flat plate, you'd hardly register a charge on it. So you roll this out and then you roll them up, and you'll see funny things happening when you go to roll up. Everything has to be insulated, and then you finish it off with a sheet of good quality wrapping paper and plenty of insulating tape. Now when you're attaching your wires at the end, you roll them around a piece of the, you roll them around a piece of the edge of the aluminium foil, or aluminum as they call it in America. So you roll it round at the edge like that, make a nice roll of it here. And then you get your wire and you wrap your wire around so that there's good contact, and use elastic bands to tighten that. Use nice little neat elastic bands to tighten the wires on the aluminum foil so there's no disconnection, so that they're securely attached to it. And this will be weak. Where this goes in here, it'll tend to tear here, so you have to be careful getting them attached. When you get the wires attached, this would be the aluminum foil, you understand? So when you get the wires attached, you need to get them wrapped around. What I did in this case, I wrapped I brought the wires over here. I didn't attach them here. I brought them right across to here and had them sticking out here, so that if they got a chuck, they had to pull all the way over to here, and that reduced the chances of damaging them where they connected. And then you have your two wires out here. So that worked. Now there's a number of things. You can get good videos on capacitors, and I don't want to be giving you too much, blinding you with science, but they're essential in modern electronics, modern electrics and electronics. We used to call them condensers. Now, if you have a battery here, we'll say this is a battery, and you take the two wires to a bulb over here. You have a bulb holder. The bulb will light if the battery's charged. Okay, you understand that? The bulb will light. If you take the wire off the bulb, the battery, the bulb will go out. If you put a capacitor across these connections here, where are they? Here, yeah. You put a capacitor across here. When you put the wire on, not only will you light the bulb, but you'll charge the capacitor as well. When you take the wire off, the capacitor will discharge into the bulb, and the bulb will stay on for a little longer. And I emphasize the word a little. The idea that a capacitor is a battery per se is not a very accurate way of putting it. It's not actually a battery. The charge put in by the battery is stored only long enough for it to discharge and for the electrons to get back to normality. If you put alternating current into a capacitor, and this is not in the books, this bit now is my theory. It's not, all the rest of it's well known. It's only the last cycle of the phase that it stores, because the phase is turning like that all the time. So clearly the capacitor cannot store both. It only stores the last charge it got. That's my theory. That will not get you marks in your exam. You might be better stay clear of it for the moment, but that's my theory. So the capacitor stores the last charge it got, and it releases it at the first opportunity. And over time it'll dissipate through inefficiencies. Now, however, they're warned that these don't dissipate too fast. So a microwave oven might have been thrown out a week ago, and you take this out, it could still whip you. That's what they say now. I don't know. Be careful with these microwave oven capacitors. I wouldn't have anything to do with them. Now, the thing about it is, if you want a direct current supply, an ordinary 12-volt battery is the job. You can use a 6-volt flash lamp battery, and they're perfectly safe. You won't get burned with them. So for kids or that, a 6-volt battery would be much safer than, the spring battery for the torches. But 12-volt battery will work as well if you're careful. They'll burn you if you get a short circuit. For other alternating current, really, the mains is one supply, but it's difficult. I don't recommend it You can put it through a 110 volt transformer, bring it down a bit, make it safer. The other thing is run the charge through a smoothing iron. It acts as a resistor, but it's not great, but you need to be careful. But anyway, I often did it. And when I mess around with mains electricity, I always mess with the neutral, not the live. So anyway, when you put an alternating current into one side of this and a bulb on the other, this will work as a conductor. So essentially, if you have a bulb there, a mains bulb like is lighting me here, and you make this a part of the circuit, in other words, the power, we'd say this is the battery. One wire goes straight to the bulb, the other one goes through the capacitor like this. If this is a battery, it won't light the bulb. It will not work with direct current. So a capacitor will not act as a conductor with direct current. With alternating current, it will. You can use it the same as the wire. So if you had the wire going direct to the bulb from the battery, you have the wire going direct to the bulb, 2 wires, the bulb will light. If you intercept this like a switch and put it through a capacitor, the bulb will light, but not as good. So capacitor acts as a conductor, but it's rarely used for that, but that's not its main function. If you put it across the two with a battery, it'll only retain the charge of the battery for a split second. It'll hold direct current, but it'll discharge it almost in a second. So if you have a little light bulb, a very tiny LED or a very tiny bulb, and you light it here with the battery, and you take away this, it'll go out. If you put a capacitor across, it will light a little longer. It will stay lit a little longer, and it'll go out. If you put alternating current to it, it'll do the same. It'll go out as well. But if you put the capacitor across, if you put the points across it, so the current this is used as a conductor, it will work permanently so long as the power is alternating. So it retains the charge for a very small time. And there's words called farad. Farad is how you gauge their capacity, and 1 farad is an enormous number. So because of that, you rarely ever see a 1 farad capacitor. It'll always be microfarads or picofarads or something like that. You'll see them in circuits. So then that's if you're ever making one. That can be done, that worked, and that's going to be dumped because it got walked on in the shed. It couldn't keep it forever. That's 10-year-old. The person that was made for it went on to be a very, very eminent electronic engineer. Now, so that's all right. That's a capacitor, and you can get them with various sizes. And Coulomb is one of the measurings. Farad is another one, and then there are all kinds of formulas, and they really would do your head in. You really have to sit down and study them. I'll tell you, it's not easy. It's a very hard discipline to pass. And that's why it irks me to see ministers in government talking about electricity. And these people have no education or never had to write anything down, and they know all. They know the whole future. And of course, the whole thing is a scam. As you know, a lot of what they're doing is a scam. So they take a perfectly well organised and made up system, and they get dug in and ruin it. And that's politics. So where would you use a capacitor on 18 minutes? One example is a bridge rectifier. When you take in this mains power here and you want to have direct current, you put it through 4 diodes, which only allow the current to flow in one direction. And the flow, instead of the power going off and on like this, it only allows it flows in one direction. But there, as you see from the original videos, there's a waveform, and there's a point in the sinusoidal wave when there is no power flowing at all, and the capacitor can absorb the height of the power and let it back in a millisecond later. And this is one of the big things about a capacitor that's not commonly said. If the capacitor discharges power immediately, you wouldn't have much use for it. It's the fact that it delays its discharge a little. So when the bridge rectifier reaches a peak, when the peak of the alternating current rises, the capacitor is charged as well as whatever it's driving. It might be a radio set or something. But then when the current collapses because of the sinusoidal wave, the capacitor keeps that going, giving a smoother, helping to smooth out the current, giving you a very close to perfect direct current. And when you're charging a battery or running a radio or something, that is very important. So that's one of the times a capacitor stores it temporarily. Now you should see that with the 50 hertz here and the 60 in America, the hertz is not picked for fun. 50 to 60 hertz is the ideal for the discharge time of the capacitor in all types of things. So that this thing about when I be talking about the frequency, that frequency is not just plucked out of the air. That has a very particular reason why that frequency is used. Now, another example, if you're in a hospital, I hope you're not doing anything in there for sickness, or some big schools, you'll see fire doors. And the fire doors are designed to close like this. And when they're opened, they stick to a magnet at both ends, and you'll hear a sort of a buzz, and that's the alternating current in the magnet. If you break the connection, the doors will spring shut. So, open, bzz, shut the connection for a second, they'll spring shut. So you can't afford to miss any frequencies or the doors could shut. Certainly 2 or 3 frequencies the doors will shut. But if you put a capacitor between them, you will probably reduce that effect to a certain amount. So the capacitor has to be chosen. Now you don't need capacitors on those fire doors. But if you had them, the effect would be that you might get 2 or 3 phases with no power, or 1 or 2 phases where the capacitor would keep it going for a split second. So it releases its charge fast, but not instantly. And when you have the 50 hertz, if you ever got a shock off the mains, you know what it is. When you have the 50 hertz, and you'll see it in those videos, you must watch those videos, 1A, 1B, and 1C. When you have the 50 hertz, the speed of the discharge of the capacitor suits it being in the center. So here's the wave, and then that's 50 per second, and the capacitor starts to give out its charge around here, meaning that 50 means that you get a smoother current. It bridges that little valley that there is. So the heavy black is the main frequency, the main 50 hertz, whereas the blue is the capacitor's discharge. So as the capacitor is charged up here, it's brought up here to this, then it's a little time factor when it releases that charge, bridging this gap here. And I've drawn a line here. So this is the time. That line, that straight line, means there's no charge at all. It's in between the phases. It's between the trough and the peak. And that's where the capacitor comes in. It supplies this piece here, smoothing out the current. For a battery charger, that's a rough example. Are you with me on that? And the 50 or 60 hertz is suitable for that. If you had a hertz of 300, the capacitor wouldn't be able to keep up with the oscillations or the change in the frequency. And if you had a frequency of 25, it would be too slow. It'd charge up and it'd be too slow. It'd be too slow. It wouldn't have its power. It'd be too late. It'd be too quick coming in as power. If the frequency is too high, it'll be too slow. So having it at 50 hertz works right for the time discharge of the capacitor. Do you understand? I know it's hard for me to explain that, but do you understand? By 50 or 60 hertz, the capacitor discharge is just when you need it in the wave. Whereas if you had different hertz, it would be out of line. Do I explain that? So now that's 23 minutes. So the other instance where you would use a capacitor, and they're used in lots of things, is in electric motors. When you have a 3-phase electric motor, you don't need a capacitor at all. The motor runs in phase with the generator, wherever that is. Runs with it. It'll run in sequence with the speed of the generator. You can alter the number of poles and alter the speed of the rotor, but you can't alter the frequency of either the generator or the motor. Now that's all right for that. If you had a 2-phase, instead of 3-phase, you have 2-phase. The 3-phase has a rotating magnetic field. Reverse the generator, the motor reverses. That's in video 1C. on Tesla. That is so important to look at. I'm not going over that again. You look at video 1C and attach it there, and try and make sure these get to students and that you have them somewhere filed so that you can give them out to someone to study them. So when you have in video 1C, you have the three-phase rotating magnetic field, no problem. You don't need capacitors at all. When you have two-phase, that's two coils in the generator, it will sort of rotate. Not as good as three. Three is the perfect one, but it will create a sort of a rotating magnetic field so that the motor is self-starting. So it has a direction given it to it, or an impetus to get it started in one direction or the other. Okay, so that's a two-phase. There's no two-phase because no commercial company supplies two-phase. But if you have a single phase, you have a problem. Your motor won't self-start. There's no rotating field. There's just an on-off, on-off. It doesn't know which way to go. Right, you can give the belt a pull and try and get it started. Once it gets up to about 70% of its normal speed, it'll run. The momentum of the motor will keep it running in the direction it's in. Okay, so you can do that, but you can't start it. So for lightly loaded applications like drill presses and light lathes and that, the load is low enough that if you can give it a pull on the belt or whatever, you'll get it started. But you can't be doing that in practical terms. You cannot sell a new machine and expect someone to pull the belt and get their fingers cut off or whatever. That's not on. So what you try to do is you try to bring the single phase machine up to a two phase. And the way you do that is you fit an extra winding at 90 degrees to the original winding. You understand? So you have your windings in the single phase here and here. The problem is when she's not self-starting, you put another winding at 90 degrees to it. But the problem is the power from the mains comes in just the same. So the top of the phase is here and the bottom is here, and that's all right. But you have nothing here. You have a null set here. So you have a situation here where you have no power at all. So you can't, there's no point having several windings in your motor if those windings receive power at the exact same time. They just get switched on and off. There's no rotation. So this is where the capacitor comes in. The capacitor stores the phase coming in and releases it down here a piece a bit later, exciting or creating a magnetic field in the secondary winding. And that magnetic field is about 90 degrees off from the one above, giving it a torque. So with the normal power, it sits there, buzz and hunk around, sits there. So it's getting activity here, but it doesn't know which way to go. And there's no momentum in it. Then you put a second winding here and you feed it delayed. You delay the current getting in here, and that creates a torque that pulls this round, and away she goes. That's a capacitor start, a single phase electric motor. And that's the way they get over the lack of their magnetic field. Some electric motors are capacitor start only. In my lathe, it's a capacitor start only. And if it's to go in both directions, you have what they call a split phase. You have two windings designed to act depending on what the way the power is fed into them with the switch. A split phase. But we not complicate that. For an ordinary drill press, you just want it going in one direction. So the capacitor delays the input of energy or electricity in here so that when this gets the pull, it brings it on round. Not as quite as efficient as the mains power. It takes some of the mains power, stores it for a split second till it gets down here and keeps this going. And that's a capacitor start. And most of them have a centrifugal switch that when it gets up to about 75% of its proper running speed, you'll hear the switch clicking out, and then it runs on the ordinary single phase once it gets the speed up. If you have other ones that are capacitor run, my drill press, and there was someone asked me there, I bought a three-phase big lump of an ignorant Ajax drill press. Oh, my machine altogether. You couldn't break it, it lasts forever. But it was three-phase, so I took the three-phase motor off it, and I put a single phase motor, and I needed a lathe to put it between centers, the rotor of the new one of the single phase, and bring it down to fit the pulley. And that's where that man is in trouble, because how are you going to get the pulley turned down? You need a lathe to turn it down. The pulleys generally will be a bit different. But anyway, there was a 3-phase on it. I took it off using this spook here. Using this spook here, I fitted the no voltage switch for the single phase. Grand job. I had to use the lathe to reduce the spindle on the 3-phase was this size. The spindle on the single phase was this size. So I had to turn this down so it fitted the pulley and work out a keyway or something on it. I forget now, I must look at it and see, but I had to, it was fixed solidly to the shaft. There's other ways to do it by putting a grub screw in. There's other ways on it, but anyway, I'll check that again for you when I'm looking at it. Now, that's the problem that man has. Now, the thing about it is, to go back to this again, this is about capacitors. The capacitor for the single phase motor allows you to shunt or to shift the torque from one single point. Now, this is very similar to riding a bike. If you are riding a bike, you have 2 pedals. You can pedal away, but only for you're capable of putting your shoe with the heel of your boot to push the pedal forward. You'd have a point where the one pedal's at the top and the other's at the bottom, and when you'd put the weight down, it wouldn't know which way to go. It could go backwards or frontwards. In machines, there's no man there to give it a wee bit of a push like that. It's up or down. So there's a point at the pedals of the bike when there's no power transmitted to the wheels. And if you were making that work with electricity, you'd need another pedal, and that pedal would need to be offset. In other words, it wouldn't want to be up or down. There'd want to be one pedal halfway up and halfway down. And then you'd need some way to store the foot power a little later, so that when it go down, it'll get the press of the pedal. So a capacitor delays the input of the electricity and the magnetic field enough to allow a rotating field, not as efficient as the 3-phase, but nevertheless a type of an imitation of a 2-phase. So a single phase motor, in a way, could be described as a 2-phase motor using the capacitor. Okay, now you can study there on them. The mathematics can be a bit difficult. You need to sit down and study them. But essentially, when you have your capacitor, if you have the plates very close together, the dielectric is usually, I use greaseproof paper in that, but usually some other substance. The dielectric reduces the efficiency a wee bit because it hinders the electrons. But it affects the voltage. It's a high science that we're not going there. But when you have the capacitor, it's the size of it matters. So for if you wanted a very big machine, if you wanted a big stone crusher, single phase, like this capacitor would need to be as big as a football pitch if it was flat, if it were flat. Now, because of that, the area of most capacitors is enormous, but they roll them up. They roll them up, thereby putting them into a smaller space. So that little tube there might be a simple capacitor. There could be 16 feet of foil in there or some other thing, and a dielectric. Do you understand? They roll them up. And this one here, I'd say if you rolled out the stuff that's in it, it could be 30 foot or 40 foot or maybe 15 meters long. Do you understand? So the whole thing is to get them compact, get them insecure where they're watertight, and just put the 2 things. Again, do not use microwave ovens, capacitors. Now, I think I've explained all that, the significance of the capacitor, and I'm very much in mind that a lot of my viewers will not be into big mathematics and all that, and there's no need to do that, just to understand. Everything in the universe, including you and I, is made up of atoms. Made up of atoms. Your car, your dog, your cat, yourself, made up of atoms. These glasses are made up of atoms. And the atom contains a proton, a neutron, and an electron. And the proton must be equal. If there's 26 protons in the atom, there must be 26 electrons spinning around. And you can drive them out by heat, and you can drive them out by an electric resistance. And when you put an electric resistance, you drive the electron out, and it'll go wherever it can, and it goes into the other side, creating an electrical imbalance. So you have too many, you have 1,000 protons here and 1,000 electrons. You put in the electricity, you shoot 200 of them over here of the electrons. Now this is not at peace, and this one's not at peace. This has too many electrons, and the minute they get a chance, they'll discharge back so they reach equilibrium. And that discharge of the electrons is so useful because, and this is what they don't tell you, because it's not instant. It's very fast, but not instant. And therefore you can use that discharge for things like bridge rectifiers, for smoothing out radio signals, etc., for all kinds of things, for music, for pop music, or all that the vibrations in the speaker are controlled by the capacitor. And you can use them then in electric motors. And a classic example of a capacitor long ago, the old cars and the old motorbikes had points. The spark was distributed by breaking the circuit of a direct current, so that the coil would collapse and give off a spark. So it was going like this. The problem with that was the points would get dirty with this constant sparking that wear out fast. So by putting a condenser, as they call it, a little capacitor, a little small fella, I have nothing really here, but little lad, maybe the size of that nut or something, maybe that size here, size of that. By putting a capacitor between the points, you took some of the power out. There was plenty of power, and stored it in the capacitor, and then released it when they joined again, and that meant that the sparking wasn't as severe. It still was enough to fire the plug, to spark the plug, but it wasn't just the full Monty, as to say, and so it prolonged the life of the points. That's all I can tell you, folks. That's my best effort at this. I'll be putting it in with that other one there, and I'll show it to you here, and they're there now for anyone. They'll be staying around and to explain this thing, because it is a fascinating subject. And when you understand all these things, and you will understand it no matter how long it takes you, then it's very hard to fool you. You know it stretches into everything: quantitative methods, money, finances, growing grass, fertilizers, everything. It's all part of chemistry. We'll see you back, folks. I don't know if any of you have stayed with me to the bitter end. You never know. I'll tell you, if some fella qualifies to be an electrical and electronic engineer, and he's on 300,000 a year, he'll never say on the street, "Do you know, I looked at your videos, only for you, I wouldn't be here at all." They won't do that. That's not how life works. But it's nice to be able to explain this. I think there are several people that are good at explaining it, but I'm better at explaining it to ordinary people. That's where I come in, the ordinary person. You don't need to be too smart or too read. It's not too smart. It's too well read up. You don't need to be after reading a big book, to understand what I'm saying. Everything's made of electrons. Everything's made of atoms. A proton, a neutron, and an electron. That is undeniably a fact. There is no doubt about that. Okay, we'll see you back. Good luck. Thank you.